Yes, it was my teacher, but
Bueno, tenemos un seminario especial de una colaboración, una colaboración internacional entre México y Israel, y bueno, para eso voy a introducir a la doctora Tamara Colangui, quien hizo su licenciatura en Derecho, una maestría en Derecho Comparado, su doctorado en Investigación Interdisciplinaria, y además ha estudiado la educación para la paz durante 20 años. Actualmente es la directora académica de la Fundación ILAN, que como dije está encargada de establecer las redes entre Israel y Latinoamérica. Además es la directora de la cátedra Shimon Pérez por la paz, la cual ha promovido la educación por la paz y la construcción de una cultura de paz por más de 22 años. Y la Fundación ILAN detecta, impulsa y promueve la innovación mexicana, ligándola con la innovación y el MINTED de Israel, donde se conjuga la relación entre academia, gobierno y empresa. ILAN promueve las relaciones entre Israel y México para establecer lazos de colaboración y poder beneficiar a México de las innovaciones y tecnologías israelíes, en conjunto con las innovaciones mexicanas, para mejorar siempre la vida de las personas. Y a continuación nos presentará un video para explicar por qué está hoy con nosotros, y luego seguirá la conferencia del doctor Amir Mehdi, que we are so happy to have you here. So,
muchas gracias, mucho gusto. Muchas gracias por recibir al doctor Mehdi aquí. Venimos de Fundación ILAN y creo que nos ha presentado Román muy bien. Tenemos un video de 3 minutos para que ustedes sepan lo que realmente hace Fundación ILAN y por qué estamos aquí. Y ya después nada más presentar en breve el currículum y la semblanza del doctor para que ya puedan empezar la conferencia.
Imaginación, liderazgo, amistad, nobleza. ILAN, Israel Latin American Network. En ILAN impulsamos la innovación, vinculados con Israel, para mejorar la vida de las personas. Israel es uno de los países con mayor capacidad de innovación en el mundo. Lo que esta nación de Medio Oriente ha logrado ha sido gracias a su cultura y a una fuente de motivación para desarrollar innovación, y que podemos describir como el triángulo de la innovación, porque une voluntades. Por un lado, la del gobierno, como promotor. En segundo lugar, las de las universidades y los emprendedores, promoviendo el conocimiento. Y finalmente, el sector privado, invirtiendo recursos. En otras palabras, autoridad, conocimiento y capital, como ejes plenamente sincronizados de un nuevo motor de desarrollo. Solo con innovación, Israel ha logrado aumentar en los últimos 30 años el PIB per cápita de $16,000 a $44,000. Todo ello solamente con tecnología, colocándolo por encima de países como Francia. Convertirse en el estado con mayor desarrollo de startups per cápita. Tener el segundo gasto más alto del mundo, 4.7% del PIB en investigación y desarrollo. Inspirados en la fortaleza de innovación israelí, nace ILAN, con el firme propósito de transformar la vida de las personas y de las sociedades en Latinoamérica con un enfoque en 7 áreas de acción: educación, salud y ciencia, comunicación, medio ambiente, transformación social, tecnología y paz. Para lograrlo, contamos con 3 mecanismos que reconocen e impulsan el talento vinculándolo con la innovación israelí. Premios ILAN. Creamos los premios ILAN a la innovación y los premios ILAN a la innovación universitaria para reconocer y motivar a los proyectos que puedan generar un alto impacto social. Delegaciones ILAN. Año con año, ILAN lleva a un grupo de innovadores en un viaje a Israel, con el objetivo de desarrollar lazos de aprendizaje entre las naciones y conocer de cerca el modelo de innovación israelí. Foros ILAN, donde los innovadores trabajarán activamente y de forma interdisciplinaria para la resolución de retos alrededor de las 7 áreas de acción. Siempre comprometidos con el cambio, proponiendo soluciones a los retos actuales para construir un futuro mejor. Albert Einstein decía, la mente que se abre a una nueva idea jamás regresa a su tamaño original. En ILAN impulsamos la innovación para mejorar la vida de las personas.
Bueno, y ahora nada más voy a presentar breves datos del doctor Amedi para que él pueda ya empezar con su ponencia. Los voy a leer en inglés para que tengan la referencia de los nombres exactamente dónde está, lo que hace y dónde estudió. So he studied at the Hebrew University of Jerusalem, graduated from there. And then he had a PhD in computational neuroscience. His thesis was visual and multicellular proceeding and plasticity in the human brain. Then he was in Harvard Medical School Center for Non-Invasive Brain and Simulation and postdoc in structural neurology. He was a lecturer and associate professor and professor of the medical neurobiology and cognitive sciences at the Hebrew University of Jerusalem. Today, he's founding director of the Baruch Heiber Institute for Brain, Cognitive and Technology at the Reichman University in Israel, and founding director at the Meyer and Ruth Rosenthal Brain Imaging Center. Doctora Medi, le damos la bienvenida.
Hi, everyone. I'm really happy to be here. Hola. It looks like some strange experiment in psychophysics with all the screen goes on off. I hope we won't be too interrupted by this. I wanted to give an overview about, you heard a little bit about my background. About 3 years ago, I moved to Reichman University, set up a new institute. And the idea here was to set up an institute that is enabled to create new technologies and then study the brain using these technologies. So what I'm going to show you today are several technologies and how we study different topics in neuroscience. I'm mainly going to speak about human neuroscience, but as you see, we are going to talk about critical periods and nature versus nurture and so on and so forth. So there is a lot of connections between this, although it might be that some of the things we found in humans are a bit different than in animals and so on and so forth, but there is a continuum here. So what I'm going to try and show you is that with the right technology and the right perceptual learning, we can do a lot of reprogramming of the brain and make big changes in the way that the brain responds to the world and to the sensory world. So in the first part, I'm going to talk about a question that interests us a lot. What happens if we are going to enable a person that never saw in his life? So he's congenitally blind. So during critical period, he didn't have any exposure to vision. And we created a new technology that's called the iMusic that enable you to represent the visual input in sounds. Okay, a little bit like ultrasound. Yeah, what is ultrasound? You have some technology that go through the belly, the sounds, and then using this you create an image. Yeah. So the idea was the same. If we can create an algorithm, and I would try to explain it to you a little bit how the algorithm works and uses music to represent vision. And now the question is, if they are going to see things like faces, like to read something, like to recognize objects using this technology, where in the brain will we see activity? Yeah. And the surprising results we got here was that in as few as a few weeks, the visual cortex starts to respond. It responds very similar to the organization that we originally have of people that did have vision in their critical period. So for example, if we are giving a object recognition task versus localization task, we get separation for the two pathways, for the ventral stream and dorsal stream. Yeah. So this will be the first part, most of the talk here. The second part of the talk, I'm going to talk about a little bit newer technology that uses the same principles. The idea that you can move information from one sense to the other side. And this is a touch technology we developed in the lab that this time transfer music, speech, and location of things in the world using vibration. Okay, so I will explain a little bit about the concept, how we do these things, and how can we use this, for example, to do rehab for cochlear implant patients, and how we can study again people that were born deaf but got some implant later in life, and how their brain adapt to it. Yeah, and I also provide some imaging work on this. So probably this will be most of the talk, and then I would mention two more projects where we have ongoing projects with much less results, but more a conceptual project. One, a project that is try to investigate why when there is anxiety and depression, there is bad feeling in the body. Yeah, people experience their emotional difficulty in the body, and on the other hand, there is more and more understanding that practices like mindfulness and meditation that uses the body, like body scan and breathing exercises on, can in turn influence our emotional system. So we found actually we were the first to map the Penfield homunculus, the body map in the primary somatosensory cortex using brain imaging, and it's very similar to the results in the animal and what found with single electrodes in epileptic patients. But we found in addition to this one homunculi, 15 more homunculi spread all over the brain, some of them in the limbic system, like insula. And using these insights, we developed new technology that are now being used, opened in a new institute to treat cancer, in which they have their physiological body markers like breathing, like heart rate, and so on and so forth, galvanic skin response connected into a neurofeedback multisensory stimulation that is while they get the cancer radiation and treatment. And it's like a new concept of trying to enhance the effect of the medical treatment using this type of sensory interventions. And finally, I might mention a new startup company we started recently, which aims to bring these insights into everyday medication. So the idea is that you would optimize your state of the body and the brain while you are taking drug or in some medical treatment. Okay, so the starting point for my talk is this image that you still open every neuroscience textbook to these days. You have basically the idea of division of labor. The different parts of the brain are devoted to different systems. And in the back of the brain, we have this 30% that is devoted to vision, the ventral stream and the dorsal stream. And then we have the auditory cortex and so on and so forth. And basically the starting point for my research was this theory of critical period. And basically what this theory says, based on the amazing work of Jubel and Wiesel, was that if you are not going to get visual experience during the first couple of weeks or months after birth, and they worked on animal models, then you are not going to develop vision, and you are not going to develop the visual cortex in a way that is having these specializations. Yeah. So, for example, as part of their studies, if you take an adult animal and you blindfold one eye or two eyes for a couple of weeks and you remove it, and you actually did it in humans. When I was in Boston, we sighted the people and put blindfold for 5 days and scanned the brain every day to see how the brain responds. But you remove the blindfold and the animal is sighted. But if you do the same trick during this so-called critical period, then if you close one eye for 1 month and then you remove the blindfold, although the photoreceptors, the neurons, the pathway, everything is fine, this eye will be blind for the rest of their life, of the animal. And if you do it for 2 eyes, the animal will be blind completely, although, again, everything physiologically is fine, okay? So this led to this theory that during sensory brain organization emerges from full exposure to unisensory in each system. In the visual system, it needs to be vision. It's the auditory system, audition. Early in life, during specific time frames, and you can argue after that, you know, if the time frame is weeks, if it's mice, maybe it's 2 years, maybe it's 5 years, yeah. But this is the concept of critical period. And what I want to show you here is a concept that, first of all, this separation between the systems and the senses are not that trivial. There is many cases that there is a lot of connections, but more importantly, so for example, we have this condition that's called synesthesia that about 5 to 10% of the people have, in which sensation from one sense, for example, sound, triggers visual sensation, yeah? And there is also many other cases like the McGurk effect and other effects in which your one sense influence a lot your perception of the other sense, yeah? Maybe the most famous everyday example is the ventriloquist effect, yeah? If you're going to watch a movie and there is a speaker in the side, your perception will be that the sound comes from the mouth of the person, because vision would capture it, although the sound comes from the side, yeah? There is many examples like this. So as I mentioned, there is also, not just in technology, but also in nature, we have animals that during tens of thousands of years developed this ability to see with sound. But this was not technology, but evolution, yeah? So for example, we are all familiar with so dolphins, some type of dolphins are one example, also bats, yeah? So we're all familiar with the topic of blind as a bat, yeah? But actually bats are not blind. They actually have vision, and they have two systems. So they switch according to the situation to have a better adaptation, evolutionary. So for example, if they're in a cave and there is light, they operate with vision perfectly fine. But if they go deeper or the night is down, then suddenly they turn off this system that sends a lot of sounds and then receive them back and analyze them at the same time in some time window and create, like ultrasound, a full 3D understanding of the environment, so they can do both the ventral stream stuff and the dorsal stream stuff. They can recognize shapes. If this is a stone, this is an insect. They could navigate in the cave and so on and so forth. Okay? So the question was, can we create a technology that enables somebody to do it when he's 50, 40? And we can test late blind and sighted, but the most interesting for us was people that never had visual experience because of this question of nature versus nurture, yeah? So we created this technology. How is it working? We take image from a camera that is on glasses. Of course, the first initial stages of the training you do in front of a computer, so you don't go around with these glasses that turns vision into sonification. And basically, we reduce the image to 1,500 pixels, so it's a very low resolution vision. And as I will show you in a second, it's also very slow vision. It's not like our real visual system. It's much lower resolution and much slower. And also, it takes a lot of time to study it, about 50 hours, 50 meetings the blind need to come. But still, if you look at the sonogram, at the sonification, you would see that this is, for example, the horse, and this is the frequency by time. You would see that the shape of the horse is maintained in these sounds. So the only question is, can we teach people to understand this? Yeah. So let me try. One of the things that are most difficult to people to understand is how is this algorithm works? How can I see with sounds? Yeah. So let's do a little example. Yeah, and let's see how good you are. We will start with one note. Yeah. One line, and let's try to draw a smile, yeah, with one sound, yeah. So it starts with a high pitch, P. Now you need to sing with me. Sing with me, P. Great, and we'll sing together the first half, and then you are alone. Okay, ready? P. Very good. Okay, so you draw a smile. Now let's do a sad face, okay? So we start with a low tone, a low pixel. D. Very good. Now let's do it in different face. I don't care, yeah? D. Beep, beep. Okay, so you sang the mouse. I ended the second line, which is the eyes. And of course, we start with very simple stimuli. Actually, we build the stimuli according to the hierarchy of the visual system. So like V1 is only lines, yeah, and intersection, V2, and so on and so forth. And after about 50 hours of training, so we add more and more nodes, yeah, and make the stimuli more and more realistic during this 50 hours of training. And after that, we are having congenitally blind, being able to perform both shape recognition and shape localization, and also even color, using this sonification method, seeing the images from the camera using sonification. Okay, so what you see here is Hamutal. She's was born blind, and she has this camera connected to a smartphone that sends it to the speaker. Yeah, that's not from them, the movie, don't worry. Yeah, and she's looking at this image and created an image in her mind eye about the shape, the location. And you see that she even opened the end exactly according to the shape of the yeah, and she can also separate even the colors, yeah, because I didn't tell you is that with the pixels, the height is according to the location in the image, but the color is according to different musical instruments that plays it. So each musical instrument has different representation. Another example is another congenitally blind. This is Sigalit, and we are now coming to her home. Again, she has these glasses and she has these headphones, and she's go and pick up her.
שימו לב לסרטון הזה, איך האישה הזו, סיגלית, עיוורת מלידה, מצליחה למצוא בין שלל החפצים שלה בבית, זוג נעליים.
Okay, so now the interesting question is what happened in their brain, yeah? So what we did was we scanned their brain before and after they learned the algorithm. I'm showing you a group results of congenitally blind, and this was very similar image to what we saw in all of them. When we present to them objects like this horse, like tools, like words, like reading, like faces, by the way, we chose 1,500 because with 1,500 you can recognize faces, individuals. I will show it to you in a second. And we scan the brain in the MRI. What's happened is very interesting. We see that initially the information goes to the blue areas, which are the auditory cortex. So this is the Heschel gyros, A1 in humans. And then it goes to the transition area between A1 and V1. And when they actually report that they recognize the object or read the word and so on and so forth, we saw that there is activity in all this visual system. Although this is congenitally blind that never saw in their life. And this is only emerges after they manage to recognize the objects. Now, I told you before that this visual is low resolution, but you still can recognize complex things like horses or face shape. But also it's very slow. So it takes them actually, as you saw in the movie, about 3 seconds to understand what is in front of them and being able to recognize and reach and find the location and also the content and grab it, yeah? So this is actually good for us because we can use a method that's called Fourier phase analysis, in which you repeat several times the same function, and it takes you each time 3 seconds. And with the phase, you can say this is early phase, middle phase, late phase, for each voxel in the brain, yeah? So basically what we saw is that here, the image is finished and they build the image in their mind eye, all these billions of neurons to this representation of space using sonification, okay? Now, in the next part, we said, actually our life, I won't show you all the results, but I will show you a summary because most of this is published. So if you're interested, you can look at it. basically our life was very simple. We went and replicated all the classic experiment in vision. Yeah. So for example, we took Ungelayer and Mishkin, a classic experiment, which you get pairs of shapes and they're the same shape or different shape, or same location, different location. And one time the task was shape analysis and one time location, and we get the separation to two streams. Or there is areas that have specializations in humans, like in animals. You have specialization for faces or for tools or for reading. So we study each specialization in different experiments. I want to show you one nice experiment because I won't have time to show you everything, but which is actually based on a Nature paper by Nancy Kenwisher from MIT lab. And she showed that in the just a little bit dorsal to the tool area, what in animals is IT cortex, in primates, yeah. You have here an area that is specialized for tools. A bit more dorsal, you have an area that responds selectively for shapes of body. Okay, but visual shapes of body. Yeah, it's called visual body area or visual extrastriate body area. Now, why this area is interesting is, first of all, it's one of the main specializations in the visual system, like the others are for faces, for navigation, and so on and so forth. Also, it's the main input into the mirror system. And the mirror system is a system that was found by Rizzolatti, which in the primates. And it's a very interesting system. It's a system that the neurons there can transfer information from visual body movement into motor action, or sensory motor action, yeah? So for example, if a baby see you do something like this, yeah, or do this, he can simulate from the vision into his motor system and do the same action, and the same neurons represent the same movements, either visually or by motor system, okay? And this system is very well preserved in evolution, so animals can do this. So for example, you can see here this kitten that is
Oh, you look like a little monkey.
So you see the movie stack, and you see that the visual image of the body is here, and the cat without language or is imitating online. And this is the action of the mirror system. It's also very important for learning, yeah. So you imitate by learning and so on and so forth. It's so preserved in evolution, is even can have this system. This is demonstrated. Now, let's now go back to be a bit serious, okay? So this is a demonstration that this is maintained in evolution and in animal models and also in humans. But if we think about it from the point of view of the critical period, then this mirror system and this body representation visually should not develop, yeah? Because if you never saw in your life, then you don't know how to transfer from vision to the motor action and back, right? So we said, okay, first of all, behaviorally, let's do this experiment. Let's give them different visual body images that are transferred to this unification method to represent space, and let's see if they can imitate. Yeah. So let's see it. You see here again.
עכשיו למשל אני מבינה שזה אמור להיות קטגוריה של גוף מלא, ואני שומעת קווים אופקים, אז אני מניחה שהוא עומד ככה.
Yeah, so she could do it immediately. And all the congenitally blind, over 15 that we tested in the lab, all of them could immediately do this transformation from this unification to the motor system, although they never had visual experience. And when we put them in the scanner, then we found out that when we have sighted doing body analysis visually, we have this specialization, this bilateral, this area that was reported by Kenwisher lab, the EBA, bilaterally more strong in the right side. This is also in sighted. And when we do the same thing in congenitally blind that never had visual experience in their life, we get 100% overlap. 100% of the subjects show activity in this right exostriate. And actually, if we put it on a standardized atlas and standardize the size and so on and so forth, we get 100% overlap in the right exostriate body area of representation of body. And when we did this analysis, the same thing, for example, for tools, then we got 100% overlap in the tool representation, okay? So and by the way, we didn't only use this technology, we also, for example, let them palpate different tools and let them palpate faces and so on and so forth, and we got the same results. So how can we explain such a strange result? So what we are arguing actually is that maybe this is only an illusion that all these visual areas are visual areas. And I want to explain why. So how can it be that when I'm palpating object or when I'm seeing an object, I see activity in the same area, and when I'm teaching somebody at the age of 50, when I'm letting him listen to this very weird sound, there is no activity there, but when they manage to, I'm teaching them to extract shape information, suddenly there is activity there, yeah? So I'm doing some overview of a lot of papers, and I will give the list here in a few minutes. So what we said, maybe this is a very interesting way to understand what these areas are really doing. So for example, for the ventral stream and for this tool area or LOC object area, we said, maybe what these brain areas are doing is reconstructing 2D and 3-dimensional geometry and shape. Okay? And now, when we have vision, then this is the most high resolution, most accurate, best sense to do this. So this is the main activity we see. But if we don't have vision and we do it by touch, we can still recognize the shape and the geometry by different cues, and you still get activity like this there. And if you learn to do it with a new technology, then with sounds, then before you know to extract the shape, there is no activity, and after there is. So it all makes sense, yeah? So what it means that actually the brain is organized according to computations and to tasks, and not according to the senses, like this classic view that you saw of Hubel and Wiesel. And you don't need visual experience then. If it works like this, you don't need visual experience. Now, of course, if vision is available, you will use it. This is the best sense. It has the highest capacity, highest bit content. It's the best modality to do shape analysis. But if you don't have it, you don't. The same thing, we, for example, studied the area next to the tool area. And this is a very interesting area. It's unique to humans. It was found by two researchers, Stanislas Dehaene and Laurent Cohen. And they found there is an area that specializes in text, in visual text. And in the beginning, it was very confusing. How could you have an area to something that was invented only a few thousand years ago, 5,000 years, 10,000 years? It's not enough time for evolution to develop areas like the face or the language area or the tools that we have tens of thousands of evolution to develop, right? So Stan came up with a brilliant theory of how this area emerges. And by the way, if I'm going to put all of you in an MRI and going to show you tools and text and faces, all of you would show the same topography. Yeah, you always have tools, text, faces. Yeah, and if I'm going to look laterally, you will have the body. Yeah, what I showed you before. So it's very consistent. Do it in China with the Chinese text and so on and so forth. So the theory was maybe there was some recycling involved. Okay, so we know about this area, for example, that it really likes line junctions. And we know about this area, or this is what they found, is that they really like the fovea and not the periphery of the visual field. So say maybe this area represents the neurons that represent fovea and line junctions. And when writing was invented, then it was recycled to process this new technology that was invented at the same time as the wheel. Yeah, it's a very important time in our civilization, because without writing, there is no culture, there is no real civilization. It's really things started to catch up very quickly with human civilization from the invention of the writing. Yeah. So when I met Stan, I told him, listen, we have all these very strange results in the blind. What do you think would happen when we let blind read Braille inside the MRI scanner and do like letters versus nonsense letters, like they do in the, or contrast reading Braille versus holding objects and so on and so forth. So there was two hypotheses. One was that the activity will be in the parietal cortex according to the sense that you acquire the knowledge. And the other option was the activity will be exactly in the same place because there is some deeper computation that we need to understand. Yeah. And what we found out is that all the congenitally blind when they read Braille, activated exactly the same area between the tool and the face area in this area, in the visual system, this visual word from area. And then if you want to think about it, like in the terms of the tools, we suggested that this is the geometry, yeah, and the three-dimensional reconstruction of it. But what is the computation here? And if you think about it deeply, you realize that actually reading is, and the language, the text invention is a multisensory creation. It's a little bit like we did in the blind when we transfer from vision to sounds, yeah? So let me try to explain. It's exactly the opposite. So let me try to explain to you what is actually writing. The first text were actually symbols that represented the whole words, yeah? Now, before writing, we could communicate, but we could communicate only using the auditory system, right? So I'm saying something, I say, okay, let's hunt this animal and have dinner, and we can coordinate. And I'm creating sound wave, and you receive them by the ear, and you understand what's going on, and you communicate. And for this, we had tens of thousands of years of evolution. This is why we got Bernica and Broca and all these language areas. Yeah. The problem with this system, it's an amazing system, yeah, the problem is that once I cannot maintain information for generations. I cannot move information for long geographic, yeah. Once it's finished, they didn't have iPhone and they couldn't record the sounds, yeah. So they needed to come up with this technology to keep it visually, actually tactilely visually, yeah, on the stone. And the first languages was like the Egyptians, you know, you have or the Chinese, you have every visual image have its own symbol, yeah, and then you read the symbol and you understand what is the word auditorily. And after that was the second jump with the invention of the phoneme. So now instead of having thousands of symbols to remember and each one for each word, it's really not efficient. You have in all the phonemic languages, which is most of the languages, you have a symbol, a visual symbol for each auditory phoneme. And you have in total like 30 symbols. And now these symbols go back, you embed the phonemes in vision, and then you go back from the symbols into the phoneme and build from the phoneme the words, from the words the sentences, and so on and so forth. Yeah. So this is a brilliant invention. It's a multisensory invention. You move information from the sound system to the visual and touch modality for the symbols, and this is actually writing. And now, if you think about it, Braille is exactly the same thing. So it's dots and it's with touch, but there is no lines and there is no line junction. There is no fovea, but you still have symbols that each symbol represents a different phoneme. And then you go back to the auditory phoneme and you read it just like cited. And this is why we get activity exactly in the same place. Okay. So again, the view is that this is a very elegant way to understand what is the deep computation there. And again, it goes against the critical period concept. Yeah. So our most recent paper, I did a bit spoiler. So this is 1,500 pixels. Can you guess who is this person? Yeah, so this is a million pixels, yeah? So you see, although it's much less good resolution, you can still recognize something about the face. And our more recent paper, we show that they can recognize different faces, and even if it's inverted or not, and there is activity in the face area. So I didn't have a lot of time to talk about this ventral dorsal separation, but we also, for example, develop a different technology that enables a blind to navigate using sounds with an electronic cane by auditory representation. And we found that the main visual navigation system in the dorsal stream is activated now with sounds, but only after learning. And it was true in congenitally blind, late blind, and also sighted that use the same touch technology. Maybe our coolest work on this respect is following the footsteps. And by the way, this is a summary of all the papers. So this dorsal ventral separation, these object tools, reading, faces, body, and so on and so forth. So if you're interested, you can take a look on this. I'm going to skip this navigation work, but I want to actually I think this is our most extreme example of how you can push this concept of adult plasticity in the absence of any visual experience during critical period. And this work was following the footsteps or a beautiful animal work from Marigan Kasser from MIT. And what Marigan Kasser did was he did a surgery on the animals where he took the basically the neurons from the eye, reroute, and instead of the pathway going from the LGN to V1, he make the neurons using sophisticated rerouting surgery and other ways, very sophisticated surgery. He made the same neurons end on A1. And what he showed is that when he's doing this, you have a development of this orientation selectivity in A1 instead of auditory selectivity. And you can think about the same thing. If you have the rerouting from the ear, you can end it on V1, and you would expect to see, or in the visual system, you expect to see now tones maps, like we have in the auditory cortex. So instead of tonotopic maps, now we have visual orientation map, and you can have like a tonotopic maps in the visual system instead of having it in the auditory cortex. So you understand? Now, this shows how amazing plasticity can be during critical period. But what we wanted to ask, if you have zero visual experience and you use it non-invasively in the adult brain, and you do the same trick, will we get new tonotopic maps in the visual system of the congenitally blind? So it's clear. How we do it, it's a bit complex. There is a beautiful method that is called population receptive field mapping, which is a method that was invented by two wonderful human visual scientists, Brian Wendell and Serge Dumlin. And basically what they showed is that if I'm going to have a, very similar to the experiment by Hubel and Wiesel, by the way, you have a line in different orientation, and this line goes into the full screen in front of the human, or in case of Hubel and Wiesel, it was the animal. And the idea is that if you have a receptive field, let's say in this location of space, let's say you can have in the fovea or you can have in the periphery, yeah? So we have the eccentricity angle, the eccentricity dimension. So you have the center, less periphery, more periphery. So each time the line, if the receptive field is here, though, so the neurons would respond each time it's passing this receptive field. And if it's like this orientation, it would fire more, this less, and so on and so forth. So you can do it actually in humans, and you move this line in all this orientation, and you look at the bold response, the response in the brain by MRI in each pixel in the brain. So you have 100,000 pixels. And what is really beautiful is that you can find not only the location of the receptive field using this, but also the size of the receptive field. Yeah. So using this, you can have this beautiful V1 maps. So, or actually the V1, V2, V3, and so on and so forth. So, for example, if you look at the dimension of the eccentricity, you will get fovea here, mid-periphery, periphery. And this is global. Any person you put in the MRI will show us the same map. Okay? So what we did, we said, okay, let's do the same trick on congenitally blind, but the lines now would transfer to our sonification method, yeah? So for example, a line like this would have, a diagonal line will have like high pitches and so on and so forth, and we span the entire soundscape field. And what is interesting is that instead of having two dimension, which is the usual dimension is how far I am from the center of the gaze. This is the periphery, center periphery, eccentricity axis. And the second is the angle. It's called polar angle. So you have actually a two-dimensional map in our brain in V1, V2, V3 that represent this two-dimension using these two axes, yeah? In our method, in the sonification method, actually the two dimensions, also we have two dimensions to represent 2D, but the dimensions are different. One is pitch, is this height of the sound. The second is time, like we did with the smile, yeah? So we use the same method, and first of all, what we found was that there is activity not only in the auditory cortex, but also massive activity in early visual cortex, and in the ventral and in the dorsal stream. But what is even more intriguing is that we found that in A1 we get this beautiful mirror symmetry tonotopic map that is actually the same in the congenitally blind and in the sighted and the hearing. Yeah, it's the same map that you have. You start with high, then low, and then high. So it's a mirror symmetry map, just like in visual system, that you have mirror symmetry maps of the space. And what is really amazing is that we find multiple new tonotopic maps that are in the visual system now, only in this blind, that are able to see using the sonification method. What was even more intriguing is that in some areas we got also time maps. Actually, we got a full map just like V1 that represent the entire 2D, and you can even decode the content of the image that is sonified. And all of this developed after it was 50, yeah, the subject, or 40 or 30 without visual experience. Anyway, so this is the take-home message, is that I will skip all this. I think you understand, is that actually the brain is organized according to computation and tasks, and actually any technology you create in perceptual learning that would give the same information, the brain can switch very quickly, because you don't need visual experience, auditory experience, and so on. Okay, in the last 10 minutes, I don't want to take too much of your time, so I will just do this part and just give you a very high-level highlight on the last part of the emotion. I think it's less relevant here. Is the same technology, is the same concept of moving information from one sense to the other, but this time in order to improve hearing impaired individuals. I would skip this part. We actually have a newer. You know what, let's see this 1 minute.
המחקרים הקודמים שלנו גרמו לנו בעצם לחשוב מה יכול לקרות אם משתמשים באותן טכנולוגיות אצל אנשים בריאים לחלוטין. האם אנחנו יכולים לקחת את היכולות הקיימות של האנשים ולהעצים אותן? לדוגמה, לגרום לאנשים לפתח שמיעת על בעזרת העברת מידע שמיעתי דרך חוש אחר, המגע. האם אנחנו יכולים לאפשר לבן אדם מצד אחד לראות את שדה הראייה הרגיל שמולו, ובעזרת חוש השמיעה לקבל מידע מעבר לשדה הראייה, וככה בעצם לפתח אצל בן אדם יכולת לתפוס את כל המרחב סביבו ב-360.
אם אני אלמד 10 אנשים חוש על מסוים, האם יתפתח אזור חדש במוח שלא היה באבולוציה? האם הם יפעילו את אותם אזורים? האם בכלל יהיה מחזור של אזורים? האם יופיע את אזור חדש? וכו'.
So this is still a work in progress, but the question here is actually it's interesting. What happened if we use this 50 hours training method and this technology, and I'm going to put the camera in the back to a sighted person, so that the back visual field that we usually don't represent in space, in vision, their eccentricity is from 0 to 180, and the map in the visual cortex in V1, V2 are from 0 to 180, yeah, from the pole into more anterior. So if a sighted person is able to see the back, will he develop like a continuation of this eccentricity map using 2 different modalities? Yeah, so it's still ongoing, but it's a nice project. But more importantly, we moved to try and create a technology that enable people that have hearing problem to represent space using touch. Now, one of the reasons we selected this is that we were very frustrated. So scientifically, this project was very interesting and very successful, like in terms of the ability to represent vision using sounds. But practically, if you want to bring it to the masses, to come for 50 meetings and do very intensive rehab, it's very problematic, yeah? And we wanted to see whether we can create a similar technology that is working very quickly, almost without learning. So we went into 2 systems that are very similar. Actually, in evolution, the hearing system conceptually is very similar to the touch system, because what we have is mechanoreceptors in both cases, yeah? But in the touch system, the mechanoreceptor works by touch or by wind and so on, or by heat. And in the ear, it's mechanoreceptors that move by this very interesting structure that moves the drum and then the hair cells in the ear, yeah? And actually, there is some animals that have super hearing because they have both the auditory system. So, for example, elephants can sense frequencies that are quite similar to humans, a bit more extended, using their ear. But in addition, they have hearing, like they can sense infrasounds, which is very low sound frequencies, using their feet. And this way they can sense, it's a bit like a radio wave, so they can hear things that are kilometers away from them. Yeah. And the same is with cricket. They have like additional mechanoreceptors on the feet that vibrates and warn them from. So what we did, you see here the cochlea in the human ear, but it's very similar also in other. And if you open it, this is actually a two-dimensional structure. The structure is vibrating according to each frequency. Sound, music, speech, actually most of it vibrates. You see here, for example, this music, almost all the So what we did, we created this artificial cochlea. So basically it's a structure that vibrates in all the frequencies that are perceivable by the touch system, so up to 200 hertz. And what we are doing is online, we do like a fast Fourier analysis, analyzing all the frequencies and the relation between them, and shifting it to the frequency that is you can accept by the touch system. Yeah. And when we did it, we found out that you can have a immediate improvement of 6 dB to your understanding of speech in a noisy environment. And if they used it for 1 hour without any guidance, just experiencing it, they can improve 10 dB. Now, what 10 dB means is, for those of you who are less auditory system or engineers, it means you are doubling the signal to noise of the speech understanding in noisy environments. And by the way, noisy environment is exactly the environment where cochlear implant patients found the most difficult to understand sound. Yeah. But we didn't stop here. We decided to create another layer of the auditory system, and this is basically to add the dimension of location. Okay, so the idea was that it's not enough to know what is the content, like in the ventral stream, what is the shape in vision, what is the content in audition. You want to know where is the sound come from. Actually, evolutionary-wise, if you walk on the street and you are hearing impaired or you're deaf, it's much more important to know if there is a car or somebody on a scooter or bike coming close to you and where is it coming from. It's less important, you know, what is of course, it's also important what is the content, yeah? So what we did, we created a stereo touch system that do an analysis of the location of the sound and give it some weighting, just like we do in the auditory system. Because in the auditory system, physiologically, we know where things come from. For example, from the left, we know because it comes earlier to the left ear and stronger because of masking of the head. And if it's from the front, it's exactly the same to the 2 ears. And if it's from the right, it's more to the right ear and earlier in time and stronger. Yeah, so we build an algorithm. It's a bit more sophisticated than this because we added also up, down, and back. But we, in this movie that I'm going to show you, had a very interesting case. It's the first time we tried it. So we first tested it on regular hearing person. It's the first time we had twins that were born deaf and got a cochlear implant surgery. So
נולדתם בעצם
חרשות לגמרי, כן.
חרשות לגמרי. למעשה זה מפגש ראשון שלנו, מישהו שעבר שתל קוכליארי. דרך אגב, איך זה היה לכם?
מגיל 4 שתל אחד, ואז אחרי 11 שנה, עברנו את השני. כאילו בגיל 14 ובגיל 3. כאילו בשני אוזניים. עד היום אני שומעת שני ערוצים שונים.
זה די מדהים, כי נראה שאנחנו מנהלים שיחה ואתם שומעות בדיוק כמוני, אבל למעשה מתחת לפני השטח קורים דברים אחרים לגמרי. אם אתם עוצמות עכשיו את העיניים, סתם סקרנות, כן?
שם איפשהו.
עוד פעם, אוקיי?
מה את אומרת?
פה? הסיבה שאתם לא יכולות לעשות מיקום כל כך טוב, זה בגלל שאוזן אחת קיבלה יתרון בגיל מאוד צעיר, האוזן השנייה רק בגיל 14, בשביל למקם דברים, אתה חייב את ההשוואה בין שתי האוזניים.
אתה יכול לראות להם את החדר שבו אפשר לבדוק איך כל הדברים האלה משתלבים?
בטח.
By the way, many cochlear
אנחנו בעצם פיתחנו פה מערכת שמיעה מלאכותית נראטת. חותכים עם 5 צלילים, והצלילים האלה זזים פה במרחב.
יש ציפור וינשוף בג'ונגל, אנחנו בג'ונגל.
נכון, בג'ונגל כזה, בדיוק. אחד מהצלילים מחובר לך לאצבעות, תתרכזי 20 שניות ותגידי לי.
ינשוף.
אבל זה לא עברו 20 שניות, איך עשית כל כך
מהר? אני
מהר?
אבל כל כך מרגיש.
מדהים, מדהים. עכשיו בוא ננסה להגיד לי איפה הצליל נמצא. תני את הראש, לפי הינשוף, עם הרטט. בוא נראה אם תצליחי. יפה.
את שומעת את הינשוף?
כן, אבל אני לא יודעת איפה.
הנה, בן מצביע בדיוק לאיפה שהראש לך מצביע.
אני חייב להגיד שזה מטורף, כי אני לא שומע מה שהיא... תקשיבו, יותר ככה, כאילו, אני מבטיחה לך שתשבי פה, את תביני מהר.
עכשיו תנסי למצוא את הינשוף בלי הרטט. איפה הוא?
לא יודע. הכל...
קרס.
עליי, לא יודעת, אני לא יודעת. כמו שתמר שומעת.
תשמעו, זה מטורף, זה מרגש רמות. בואי תשבי פה.
So they didn't have any auditory experience during critical period to localize things. But once they put it on the finger, suddenly it's working.
יפה, יפה, מדהים. את עושה את זה מושלם. מי אמרנו יותר מתעניינת במוזיקה?
אני.
תנסי לשבת על זה. אנחנו בואו להשמיע את הסימפוניה התשיעית של בטהובן, שחלק מהמוזיקה מוקרן ברטט. אני מאוד מסוקרן.
מעניין. זה כאילו, את עצמו איזה כלים נמוכים, ודודודום, בתחת פה. מהמם.
כן?
הרגיש לי שאני בתוך הקונצרט. יושבת איתם על הבמה כזה. וואי. זה יותר מכניס אותי לחוויה. השמיעה שלי סבבה, אבל אף פעם לא הרגשתי 100%. אולי זה החלק שמשלים את הלוח הפאזל שאני חסר, כאילו להרגיש את השלמות יותר.
זה מאוד מרגש לראות שיכול להיות לזה רלוונטיות גם לעולם של מושלי שמיעה, של אנשים בעוד שמיעה.
So as you saw, we were a bit excited because actually we didn't know it would work with cochlear implant patients, so it was very emotional to see it. Just to mention, it's not just for people with hearing impairment. We had recently an experiment with this special ambisonic room that enabled you to program the location and test them very accurately. We had hearing people that tested for localization in the hearing system. So what's the resolution? And then we did another experiment using just the touch, and we showed that you can, in less than 1 hour of training, reach the same ability to localize things in space using this new stereo touch system. So I think I would finish here. Maybe I will just take 2 more minutes to mention that this idea of using technology or reprogramming and looking at the brain as a multisensory and influence things is not only important for sensory systems and rehab of sensory systems, but also for the emotional systems, for things like pain, like anxiety, like depression, and so on and so forth. So this is why these days we are, together with Professor Ben Korn, opening a new institute for cancer that have this ability to influence your pain or your emotional state using sonification in 3D of sounds, of vision, and so on and so forth. Now it sounds a bit strange, and this is this new building, and you would see in a second the visual rendering, like what the patient experienced. But I want to finish maybe and leave you with this concept to show you how even high-level things like emotion, like pain, and so on and so forth can also be influenced and reprogrammed using the senses. Yeah. So the story is about unfortunately an accident that happened a lot in construction sites. Yeah. So there is construction all over the world and many construction sites, and you get many times these terrible accidents in which a big nail go into the foot, and this is really terrible pain. The strong guy fall on the floor and cry, and of course there is ambulance, and they get him to the ER, and he gets morphine and surgery and so on and so forth. But this is, okay. So this is why do you tell it this us? Yeah, because this is terrible pain. So apparently there is several papers in several medical journals that reported that in some cases, when these task construction guys got into the ER, they opened the shoes, they tried to do the surgery, they realized actually the nail came between two fingers and actually didn't touch the body. It's just the visual representation and the mindset that I'm having a terrible thing that caused them like immense pain and they would rush to the ER. Yeah, and it was reported in several independent. So our concept is, okay, so maybe you can influence it in two directions. Yeah, maybe the visual input can also influence the pain and anxiety and claustrophobia and so on and so forth. So this is why I created this. I won't get into the details, but took several methods that you can use neurofeedback and visual audio and to reduce anxiety and claustrophobia and pain. And you see here the radiotherapy where they get the treatment for cancer and have this amazing screens and so on and so forth. So, and by the way, this was true also, you know, there is a famous experiment by Ramachandran showing that phantom pain, if you use a mirror box and you project the vision onto the phantom pain, you can make it, the pain disappear and so on and so forth. So I think we are entering, and this is where the new company enters, we are entering a very interesting period where using technology, we can improve the way we are doing different rehab, if it's in the visual system, it's in the audio system, if it's in pain, and if it's in how we treat people in hospitals and so on and so forth. So that's what I wanted to share with you today. Thank you very much for having me here and in your beautiful country. Yeah, thank you. Gracias. Yes.
I'm wondering what type of connections are there that can be used for transferring information from auditory to visual in adult people?
So it's very interesting. First of all, people didn't study it enough, I think, but there is a few researchers that studied this, and we know several things about it. One, we know that during development, there is much more connection between all the brain areas, and these connections are getting sorted less and less and less while the child and the baby is developing. But still in the adult, there is residual connectivity between, you know, if you put in injection in neurons in A1, you will get labeling in also in retinotopic visual areas. So Kennedy, for example, have a beautiful work on this in animal models. And what our view is that actually, that's also what we saw in the blindfolding experiment, is that once you don't have the input from one sense, this weak connection, because of Hebb rules, are getting strengthened and resurfacing back. So this is the mechanism we think this is work on. And it's supported, for example, I told you a little bit about the study with reading. So what we did in this study, we took people that are, again, never had visual experience, and we did experiment in which we had the Roman numerals. So, for example, V, X, L, and so on and so forth. And we color them in different colors, so different music and instrument play them. And we scan their brain before they learn the algorithm and after to represent the symbols and the phonemes. And we gave them different tasks. So we gave them 3 different tasks. One task was to tell us what is the phoneme that corresponds to this sonification. The second was to tell us what is the quantity. So it's the same input, but now they need to take 5, 10, 50, and so on. And the third, they need to analyze the timbre and tell us what is the color. And in the second experiment, we used a method that is now used a lot in clinic and also in neuroscience, human neuroscience, called resting state connectivity. The idea is that you can see the functional connectivity between brain areas when the human doesn't do anything. It's just lying down for 10 minutes. And the idea is that if there is some fluctuation activity in neurons and in brain areas when you are at rest, and if there is a fluctuation up and there is a connectivity, so also the connected area will go up because of the neurotransmitters. And if it goes down, and so on and so forth. And we found that there is a connectivity from the left. So we found that the reading is in the left and the number is in the right, in the same visual so-called area. And then the left side is connected to the phoneme region, both in sighted and congenitally blind, and the number is connected to quantity maps in the parietal. So it's another demonstration that probably there is some connection that can get strengthened and enable this crosstalk. And in some cases, we think we showed, for example, there is connection between the hand area and the tool area that we argue it's actually a tool three-dimensional rendering of geometry and of objects in on modality. So you must have also this connectivity from the hand area to the tool area, which is actually multisensory, not just visual. But still, there is not enough research, and definitely not enough in animal to really look at it deeply.
But the idea would be that these connections exist, but are silent.
Or weakened, or for example, in the case of the connection between, just people never looked at it, you know. In the case of, for example, the hand area in the homunculus and the tool area of the visual area, it's also not in the blind, in the sighted, it's there. And when sighted touch objects, we had a Nature Neuroscience paper on this, you get activity in this tool area. So it's really probably supporting reconstruction of 3D regardless of the sense. It's just more dominant for vision because it's more accurate, more accessible, work more long distance.
Blindness can have different origins.
Yes.
Can your experiments work in any of them?
Well, over 95% of blindness is because of problems in the periphery. Yeah, so it's either in the retina. So, for example, you can have in the delivery the photoreceptors and the neurons are too far apart, so there is no communication. So you're blind. It can be because of a tumor in LGN. You have different reasons, but most of the reasons is because problems in the periphery, like in the periphery, not in the cortex. You have less than 5% that is because of this. We never tested someone that is cortically blind. It's relatively rare, and definitely not congenitally, which is our interest. My guess is with them it will work less good. But good questions. Thank you.
Thank you very much. It was really nice and impressive your talk.
Gracias.
Just curious about one of the things that you mentioned when you were talking about the examples of the dolphins and the bats that they can
switch between the systems. Yeah,
exactly. That is my question. You mentioned that they can switch, like they can shut down one system.
Right.
So that is what I am impressed. Do you know how it is done? Because we cannot shut down. We cannot stop feeling or stop hearing.
No, I didn't mean that they consciously shut down the visual system. What I meant is that they have two parallel systems. When there is light, they use their eyes to eat and to avoid the stones and to navigate. And when there is no light, they use the other system.
Okay, but they are still able to respond to the visual system.
Yeah, but if it's dark, they cannot respond, so they can only use the other system. But they don't. It's not. First of all, I don't know what the animal is feeling. Yeah, I don't know what they.
Yeah, no, I didn't mean.
But yes,
I
yes,
thought that you could
yes.
give it like a circuit or something.
Right. Yeah. So it's completely different circuits that do this very different analysis. Yeah, because they need to actually analyze the changes in the frequencies, and this is also why they have very unique ears. If you look at the shape of the way, for example, humans do up down. What we found in the lab in Reichman University in this special room, that we can look at the just noticeable difference. It's very good in the horizontal, and it's very bad up down. It's not that great up down in humans, and it's very bad up back. So if you look at the J&D, the just noticeable difference, the way you do this is by comparing the two ears. The way you do up down is by looking at distortions of many frequencies, and when things come from up and interact with your own ear, if I'm going to switch your ear to a different ear, it won't work. It's collapsed to zero. So they have a very unique ear, and they do analysis, very similar analysis or a lot of sounds over a window of time, and this is how they're able to do it. So it's completely different neural circuits, if this is what you're hinting for.
Thank you.
Hi. Thanks for the nice
by the way, just to add one more thing, I think the movie was not that clear about the super sensing. So one of the questions we ask now, and I still don't have results, but actually we have behavioral results, but not brain imaging results yet, is can we develop, like bats, to have the two systems in parallel, so both vision and to be able to do it, and how would be represented in the brain and relates to each other. So for example, if I'm being able to see something here with the simplification, how it relates eccentricity-wise to the visual map that we have in the brain and so on. Just to, sorry. Yes.
Yeah, so very fascinating, the story. I've been thinking about, I work with proteins and, and how the proteins work. And there is a way of seeing things in proteins that now people are thinking that the way in which proteins work is by making vibration. So if they vibrate in a particular way, then they can do certain things, and if they don't, then they change to do some other thing.
Wow.
So what you're saying is basically the same thing. So it's I have imagined that the body is so life is a matter of how do you pack things. If you pack correctly things, then things work correctly.
Yeah, if you're referring to that, what we try to do is to pack things a little bit differently, so information that is missing is now accessible. So it's a very nice analogy what you're referring to.
So what I see that you're doing is that the sound that you're using is affecting the whole system, and the system then can respond in the way that you want.
Yeah.
But then I'm wondering, for example, in the connection between the brain and the gut is well established. And if you have someone that is born blind, I'm sure that the gut, the microbiome, should be changed as well.
That's a beautiful research question that I don't think anyone studied. And in general, I would say that there is now more and more interest. There is a second nervous system in the gut, and the connection between this nervous system and the brain is, I think it's actually understudied dramatically. And this is one of the reasons we see all this connection that I told you about this body representation in limbic, in emotion areas, and but frankly, I was a bit disappointed. We published these papers, the first paper in 2012 in PNAS, and then 2 papers in J Neuroscience about these multiple maps, and some of them in the emotion system. And I'm not, I was very lucky, and our papers are highly cited, and over 10,000 citations and under paper, but these papers are completely ignored. I don't know, and they're in good venues. People don't study them. It's not, I think it's completely understudied, all this connection between the body sensation, the gut, on the body itself, and the emotion system, and all this. And this is critical. We are living in a period which it's a pandemic. It's another pandemic. This mental health pandemic, if I may. And we should study it much more. And I think also there is a lot of potential, and that's what we started to do more and more in the last year, to improve treatments by also not just taking drugs and see how it affects the body. This is one part of the equation, it's a very important part, but also you can have connections from top down that would influence your healing process and your recovery. And even today with virtual reality, we can, for example, trigger the release of endorphins, and that can work with the morphine and reduce pain. And we can have all this visual and audio effect to reduce pain and so on and so forth. So it's only the beginning of the story, I think. And I hope this is studied much more and would be a major topic, as much as I love sensory systems, and I love them, yeah. Okay, thank you so much or unless there is more, okay.